We will continue with our lectures on linear algebra for data science. Today I will talk about hyperplanes, half-spaces and eigenvalues, eigenvectors and so on. Let us start this lecture with hyperplanes. Geometrically, hyperplane is a geometric entity whose dimension is one less than that of its ambient space. So, what this means is the following. For example, if you take the 3D space, then hyperplane is a geometric entity which is one dimension less. So, it is going to be 2 dimensions, and a 2-dimensional entity in a 3D space would be a plane. Now, if you take 2 dimensions, then 1 dimension less would be a single dimensional geometric entity, which would be a line and so on. The hyperplane is usually described by an equation as follows. If I expand this out for n variables, so I will get something like x1 n1 plus x2 n2 plus x3 n3 and so on, xn nn plus b equals 0. In just 2 dimensions, you will see that this is x1 n1 plus x2 n2 plus b equals 0, which is an equation of line. We have seen before the idea of subspaces. Hyperplanes in general are not subspaces. However, if we have hyperplanes of the form x transpose n equal to 0, that is, if the plane goes through the origin, then an hyperplane also becomes a subspace. Now that we have described what a hyperplane is, let me move on to the concept of half space. To explain the concept of half space, I am going to look at this 2-dimensional picture on the left hand side of the screen. So, here we have a 2-dimensional space in x1 and x2, and as we have discussed before, an equation in 2 dimensions would be a line which would be a hyperplane. So, the equation to the line is written as x transpose n plus b equal to 0. So, for in this 2 dimensions we could write this line as, for example, x1 n1 plus x2 n2 plus b equals 0. While I have drawn this line only for part of this picture, in reality this line would extend all the way on both sides. Now, you notice the following. You see, when I extend this line all the way on both sides, then this whole 2-dimensional space is broken into 2 spaces, one on this side of the line and the other one on this side of the line. Now, these 2 spaces are what are called the half spaces. Now, the question that we have is the following. If there are points on one half space and points on the other half space, is there some characteristic that separates them? For example, can I do some computations for all the points on one half space and get some value, and some computation for all the points on the other half space and get some value, and use that to make some decisions? And that is the reason why we are interested in this half spaces from a data science viewpoint. So, this question is of importance in a particular kind of problem called a classification problem. Let me explain what that means. In fact, we are going to look at a very specific classification problem called binary classification problem. So, let us assume that I have, let us say, in 2-dimensional space data belonging to 2 classes. For example, let us say I have data belonging to class 1 like this, and I call it class 1, and then I have data belonging to class 2 is something like this, call it class 2. So, this classes could be anything. So, for example, this could be a group of people who like South Indian restaurants, and this could be a group of people who do not like South Indian restaurants, and the coordinates x1 and x2 could be some way of characterizing people in terms of some attributes of these folks, let us say, who have taken a survey to say whether they like South Indian food or do not like South Indian food. Now, what we want to do is, if I give you the attributes of a new person, let us say that attribute falls here, and then I ask you this question as to would this person like South Indian food or not like South Indian food, and the answer would most likely be that this person will not like South Indian food, because this data point is very close to class 2. Whereas, if I gave you another point here, for example, then you would come to the conclusion this person is likely to like South Indian food. So, what we want to do is we want to be able to evaluate cases like this. So, we want to somehow come up with a discriminating function between these two classes. So, one way to do that would be something like this: draw a line between these two classes, and then say if there is some characteristic that holds for this side of the line, which is what we called as a half space here, and if there is some characteristic that holds to this side of the line, then we could use that characteristic as a discriminant function for doing this binary classification problem. So, that is the data science interest in understanding this topic in linear algebra. Now, let us proceed to see how we do this through some simple geometric concept. Let us go back to this picture and then ask the question as to how do I determine which side of a half plane or a half space, which half space does a point lie in. So, to understand this, what we are going to do is we are going to take 3 points as shown here, x2, x1 and x3, and ask the question as to how do I distinguish whether the point is on a line or to one half space or the other. So, the way we are going to do this is the following. We are going to first look at this in little more detail, and we know that when I write an equation of the form x transpose n plus b equals 0, n is normal to this line, is something that we have already described. However, there is an important point to note here. The normal could be defined in 2 ways. One is the normal is in this direction. The other thing to do is to just take the opposite direction and then define a normal in this fashion also. So, it is important to know in which side normal is defined. To understand this, for example, if I say this is a normal for an equation which is x transpose n plus b equals 0, if I simply multiply this equation by -1, then I am defining a normal to the other side. So, this is an important point to remember. Now, what we want to know is where do these points x1, x2, x3 lie. To do this, what we are going to do is we are going to evaluate a discriminant function or a function which is basically the equation of the line. So, what we want to do is we want to understand what this will be, what this will be, and what this will be. Now, when we look at point x1, we know that the point lies on the line. So, this is going to be 0. So, this is straightforward. What we are interested in is what happens to this quantity for x3 and x2, and is there some way in which we can say that every point to one side of the line will have the same characteristic and every other point on the other side of the line will have a different characteristic. So, to do this, let us first look at x3 transpose n plus b and then see what happens. So, I want to know what this is. Notice in this picture I have defined a new point x prime on the line, and then I have another vector which goes from x prime to x3. Now, x3 is the vector that goes from here to here. From vector addition, we know that I can write x3 as x prime this plus this x prime plus y prime. So, what I am going to do is I am going to simply substitute this into the equation and then see what happens. So, I am going to have x prime plus y prime transpose n plus b. This is what I want to evaluate. This will become x prime transpose n plus b plus y prime transpose n. All I have done is I have moved b closer to this term to show you something. Now, notice what happens to this term right here. Since x prime is on the line and the equation of line is x transpose n plus b, this has to go to 0. So, when we compute x 3 transpose n plus b, we are simply left with this term right here. And if you notice this term, you would see that this is a dot product between this vector and this vector. And the most important thing to note here is the following: as long as the point lies to this side of the line, then you would see whatever point you take, the angle between that point and the normal would be in the following ranges. So, you take any point, this side or this side. So, the angle between the normal and that point is going to be the following. So, supposing we look at this and then say, okay, I am going to do this angle in this direction, right. So, what you are going to notice is the following: if the point is between these two, then I am going to have a positive theta angle. Now, the way you do this is the following. So, you go like this. So, for this quadrant, if you start with 0 here, for this quadrant the angle is going to be between 0 and 90, and for this quadrant the angle is going to be between 270 and 360. So, if a point is this side, the angle between this vector and this normal is going to be between 0 and 90, and if the point is in this side, the angle is going to be between 270 and 360. We also know that when I have dot products A transpose B, I can also write this as magnitude of A, magnitude of B, cos theta, where theta is the angle between these two vectors. So, we look at all the points up to here. So, whatever is a point, you have these angles, and all of these angles are between 0 and 90. So, for any point between here and here in this whole space, you are going to get AB some angle between 0 and 90, and we know from our high school rule, all silver teacups, cos theta will always be positive. So, A transpose B is going to be positive, that means this is going to be positive. Now, when you get to points here, then the angles are going to be between 270 and 360, which is in the fourth quadrant, again using the same rule, all silver teacups. The fourth quadrant is C, cos, so cos is going to be positive. So, again you have A transpose B being positive. So, irrespective of where the point is to this side of the line, I am always going to get, when I take this x 3 transpose n plus b, I am always going to get a positive value. Now, by similar argument, you can say for any point on the other side or the other half space, the angles are going to be between 90 to 180 here and 180 to 270, and as we know, cos theta for angles between 90 to 270 is negative. So, any point on this side of the line or the half space, the computation x 2 transpose n plus b is going to be less than 0. So, this is an important idea that I would like you to understand. So, what this basically says is the following: if you were to simply take any point that I give you and then I evaluate x transpose n plus b, if that point is on the side of the normal half space, then x transpose n plus b will be positive, and if it is on the half space in the opposite side, then it is going to be negative. And I already told you how this is important from a data science viewpoint. So, let us consider simple 2D geometry, and then let us take n as 1 3 and b as 4. So, this would give me this equation for x transpose n plus b. Now, let us say I take a point on 3 points for example. So, let me consider minus 1 as 1 point. Let us also consider 1 minus 1 as another point, and let us consider 1 minus 2 as another point, and then see what happens. So, when I take the point minus 1 and I substitute into this x 1 plus 3 x 2 plus 4. So, it will be minus 1 minus 3 plus 4. So, the point 1 minus 1 will lead to minus 1 will lead to 0. So, that means the point minus 1 is on the line. When I take the point 1 minus 1, so this is going to be 1 minus 3 plus 4. So, this is going to be 2, so positive. So, this is on in the positive half space, and when I take the point 1 minus 2, then I am going to get 1 minus 6 plus 4, which is going to be equal to minus 1 less than 0. So, this is in the negative half space. So, this is on the hyperplane or the line, this is on the positive half space, and this is on the negative half space. So, that tells you how to look at different points and then decide which side of the hyperplane or which half space these points lie. Now that we have understood hyperplanes and half spaces, we are going to move on to the last linear algebra concept that I am going to teach in this module on linear algebra for data sciences. And once we are done with this topic, then we have enough information for us to teach you the various algorithms, commonly used algorithms or the first level algorithms in data science. So, let us look at this idea of eigenvalues and eigenvectors. We have previously seen linear equations of the form Ax equal to b. We have looked at it both algebraically and geometrically. We have spent quite a bit of time on looking at these equations algebraically. We talked about when these equations are solvable, when there will be infinite number of solutions, how do we address all of those cases in a unified fashion, and so on. Now, what we are going to do is, now that we know about vectors and so on, we are going to look at a slightly geometrical interpretation for this equation again, and then explain the idea of eigenvalues and eigenvectors, and then connect the notion of these eigenvalues and eigenvectors with the column space, null space, and so on that we have seen before. So, this is very important because these ideas are used quite a bit in data compression, noise removal, model building, and so on. We will start by starting here saying I have this Ax equal to b, and A is an n by n matrix, x is n by 1 and b is n by 1. So, this is the kind of system that we are looking at. So, we are going to only look at square matrices n by n. Now, you can think of this as n equations and n variables. There is also another interpretation you can give for this, which is the following. Supposing I have a vector x, something like this, and if I operate A on this, so by operating I mean we define an operation as pre-multiplying this vector by A. So, let us say I operate A on this vector, which is Ax, then I notice from this equation I get B, which is basically some other new direction that I have. So, you can think about this as the following. I can think about this as a equation which tells me that when I operate A on x, then I get a new vector B, which is in a different direction from x. So, this is a very simple interpretation of this equation Ax equal to B, which is what is written here. X, I send it through A and I define sending it through A as pre-multiplying by A. So, A times x equal to B. Now that we have this interpretation, we ask the following question: for a matrix A, are there some directions which when you operate this A on, they do not change their orientation? In other words, I want to know if there are x vectors for matrix A such that when I operate A on x, I get lambda x, not B, lambda x. Here the idea is, because this is x, there is no change in orientation save a multiplication by a scalar. Now, this multiplication scalar could be positive or negative, in which case we are talking about the following. So, if this is x, so when I operate A on x, since it is in the same direction, it is either this way or this way, and if lambda is positive, it will be in this direction, and if lambda is negative, it will be in this direction, and so on. So, the question is, would there be directions like this for all kinds of matrices? Is an interesting question that you could ask. For now, let us focus on lambda being positive. Lambda can be negative also. If lambda is positive, then we see this equation and then notice that if lambda is less than 1, then basically when I operate A on x, the vector actually shrinks. Okay. So, if this is x, if lambda is less than 1, this will be shrunk like this, and if lambda is greater than 1, it will be at a higher magnitude than the original x vector. Now, the question is, for every matrix A, would there be vectors like this x, and what would be the scalar multiple, and what is the use of all of this is something that we should also address at some point as we go through this lecture. Now, let me give you some definitions. This x are called the eigenvectors and lambdas are called the eigenvalues corresponding to those eigenvectors. So, the questions that we are left with are, how do we find out that every matrix, whether it would have eigenvectors, and how do I compute this eigenvectors and eigenvalues? So, to compute the eigenvalues, we follow the procedure that I am going to outline now. So, the original equation is Ax equals lambda x. What I could do is I could bring this lambda x to this side, and then I get this equation Ax minus lambda I x equals 0. So, this becomes A minus lambda I times x equal to 0. Now, notice that this is basically a vector equation, because I have n by n vector, this is n by 1. So, I have on the left hand side n by 1. So, I have a vector here and I want zeros here. So, I want to find an x such that this is true. Now, we have everything that we need to solve at this equation. So, what I am going to explain to you is the following. If I want to get an x which is not all 0, notice that if x is all 0, this is a solution, right. So, x equal to 0 is a solution, but we are not interested in this solution because this is what we call as a trivial solution. We are not interested in this, we are only interested in solutions that we call as non-trivial. At least one of the x's will have to be non-zero. Now, notice that if this equation is solvable, then x is in the null space of A minus lambda I matrix, This is something that we have seen before while we define the null space. And we also know that the rank nullity theorem says the rank of the matrix plus nullity equals n, which is the number of columns. We are looking at square matrices, n by n matrices. Now we know that if there is even one vector x such that this is 0, that means the rank of the null space is at least 1. And since the rank of the null space is at least 1, nullity is at least 1, that means the rank of the matrix has to be less than n, right. It cannot be n. If this is n, nullity is 0, that means there are no non-trivial solutions. So if there needs to be a solution for x, then we know that the rank of the matrix A minus lambda I has to be less than n, that is the matrix A minus lambda I is not a full rank matrix, and we know that if the matrix is not full rank, then the determinant of that matrix has to be 0. So in summary, if we want a non-trivial solution for x, then that necessarily means that this determinant A minus lambda I has to be equal to 0. Now once we solve for this equation and compute a lambda, then we can go back and then substitute the value of lambda here, and then we have A minus lambda I times x equal to 0. The way we have chosen lambda is such that this matrix does not have full rank, that means there is at least one vector in the null space, and using concepts that we have learned before, we can identify this null space vector, which would become the eigenvector. Let me illustrate this with an example here. Let us consider the matrix A, which is 8, 7, 2, 3, and let us compute this determinant A minus lambda I. So you get the following equation and you get a quadratic equation here. Notice an interesting thing here. If I have an n by n matrix, the determinant in lambda would be an nth order polynomial. In this case, I have a 2 by 2 matrix, so the determinant is a lambda function which is a quadratic, and if it is 3 by 3 it will be cubic and so on. So this opens out the possibility of a solution to this equation being complex also. So this is an important point to note here. Though your original matrix A is real, the solution to your eigenvalue problem could be either real or complex depending on the polynomial that you end up with. In this case, we have chosen this example in such a manner that I get two real solutions, and the real solutions are 10 and 1. So I can easily see that this equation has solutions 10 and 1. So that means I have two eigenvalues, lambda 1 equal to 10 and lambda 2 equals 1. Now how do I go ahead and calculate the eigenvectors corresponding to these eigenvalues? So let us illustrate this for lambda equals 1. So I take this eigenvalue eigenvector equation. Now that I know lambda equal to 1, this becomes 8, 7, 2, 3, x1, x2 is x1 plus x2. Now this turns out into these two equations, and if you notice, you take the first equation is 8x1 plus 7x2 equals x1. So if I take x1 to this side, I get 7x1 plus 7x2 equals 0, which is the same as x1 plus x2 equals 0. If you take the second equation, you will see that it is 2x1 plus 3x2 equals x2, which basically says 2x1 plus 2x2 equals 0, which also is x1 plus x2 equals 0. So both these equations turn out to be the same. Now any solution where x2 is the negative of x1 would be a eigenvector. What we do is the following: of all of those solutions, we also make sure that we get an eigenvector which has unit magnitude. So if you notice here the eigenvector that we get, you notice that x1 and this is x2, and you notice that x2 is minus x1 or x1 is minus x2, which is what will satisfy this equation. And instead of picking any k minus k as a solution here, we pick a k in such a way that the magnitude of this vector is 1. So, we know that the magnitude of this vector will be 1 by root 2 whole squared plus minus 1 by root 2 whole squared root, which will be root of half plus half, which will be root of 1 equals 1. So, that way we make this a specific eigenvector which has unit length. We could do the same thing for lambda equal 10 by much the same procedure. You will notice that you will get this equation here, 7x2 is 2x1. So, basically what you could do is any vector which is such that if x1 is k, x2 is 2k by 7 would satisfy this equation. However, what we do is we choose this k in such a way that the magnitude of the eigenvector is 1. So, in this case 7 by root 53, 2 by root 53. If you do the magnitude of this, you will see this is going to be root of 49 by 53 plus 4 by 53, which will be root of 1 equals 1. So, you see that the magnitude is 1, and also this equation is basically satisfied by any eigenvector which is of this form k 2k by 7. So, in summary, for the eigenvalue eigenvector portion of this lecture, we started with Ax equal to b, which has a geometric interpretation of A operating on x giving a new vector b. Now, if we force this b to be lambda x, some scalar multiple of x itself, where the scalar multiple could be either positive or negative, we get the eigenvalue eigenvector equation. And to calculate the eigenvalue, what we do is we calculate the determinant A minus lambda I, set it to 0. For an n by n matrix, there will be an nth order polynomial that we need to solve, which opens out to the possibility of the eigenvalues being either real or complex. And once we identify the eigenvalues, we can get eigenvectors as the null space of A minus lambda I, where lambda is the corresponding eigenvalue. In the next lecture, what I will do is I will connect this notion of eigenvalues and eigenvectors to things that we have already talked before in terms of column space and null space of matrices and so on. We already saw that the eigenvectors are actually in the null space of A minus lambda I. I am going to develop on this idea and then show you other connections between eigenvectors and these fundamental subspaces, and I will also allude to how this is a very important problem that is used in a number of data science algorithms. So, I will see you in the next class. Thank you.